So my name is Chen from Johns Hopkins University. My talk today is physical interaction with obstacles helps in motion planning and control. So when current man-made locomotors encounter with obstacles, their method is mainly to avoid all obstacles. So they first create a geometric map of the environment and then use it to do motion planning and control. But in some harsh situations, the obstacles are too dense to avoid, so most locomotors fail to traverse. However, when animals move on complex terrains, instead of avoiding, it's very common to have many physical interactions with obstacles. For example, in this video, the cockroach keeps interacting with dense grass, and the interaction forces are relevant to the material properties of the obstacles, like the stiffness of the grass here. So to better traverse with a physical interaction, we need a map that contains the physics, such as material properties. In previous study, we have done cockroach experiments about traversing beams with different stiffness. When the cockroach encountered two different beams, if the beams are soft, the cockroach simply push down beams and traverse. If the beams are stiff, the cockroach first hit on beams, and during the short contact, it realized it could not simply push down them because it requires higher forces and more energy. So it changed the strategy. It slowed down and rolled its body to traverse the gap. The physical interaction with the beams is important in this process. First, it helps the cockroach to know the environment and choose a better traversal strategy. Second, when it rolls its body, the physical interaction with beam helps it to roll. Inspired by cockroach traversal, we made a physical model and designed a robot setup to better understand the mechanism and leverage the physical interaction to traverse complex terrains. And I will focus on the physical model in this talk. We don't know what animals really do during traversal, but we made a demo experiment to demonstrate the possible procedure, and we can apply this procedure to robots. Here is the demo experiment we make. The body is driven forward by a propulsive force, and we also added some Gaussian noise in angular velocities along roll and pitch directions to model the noise in environment. And we have run 20 trials to show the representative of our results. When the body contact beams, it can sense the total forces during interaction. In the model, we assume the contact forces are normal to the contact surface. It also senses the positions of body and beams every moment, so it can create a geometric map first. Force sensing helps the body know the stiffness of beams, so combining the material properties and the geometric map, we can plan the motion. It costs time in these steps, and we name it as sensory motor delay. The final step is to control the body to follow the planned trajectory. To simplify the model, we made some approximations. For the body, we assume it is an ellipsoid rigid body, and we constrain the translation in x direction and the rotation in roll and pitch directions to have fewer degrees of freedom. For beams, we assume it is massless and has no thickness. Each beam consists of two rigid segments with a torsional spring in the middle. The bottom segment is upright and its length delta h is constant. So the beam model has two unknown parameters, the stiffness of the spring and the base length. Both of them can be solved from forces during contact. For contact, we approximate all contact is quasi-static and ignore the frictions between the beam and the body. We prescribe the beam model using stiffness and delta H, which are unknown to the body before contact. From model, we can calculate forces that the beams exert on the body. We added some Gaussian noise to the beam forces to simulate the real forces that are noisy. The body can then measure these beam forces as it comes in contact with the beams. So we know the positions of the body and beams, And from force sensor, we also know the contact forces with the beams. So we can use this information and the simple dynamic model to solve stiffness. First, we set stiffness and the base length of the beam as unknown variables K1, K2, and delta H. Second, we derive the functions of forces from the model with these variables. Third, we define the error function to sum mismatch between the measurement forces and the modeling forces. At last, we minimize error function to get the best estimates for these parameters of the model. For example, in the demo experiment, we solved the stiffness and delta H from the contact forces. And the solved value we can see here is very close to the real values. We hope the robot has the least resistance in the traversal. So in motion planning, we choose the trajectory that has the lowest potential energy barrier. By adding material properties into the geometric map, we made a potential energy landscape of the body. The potential energy consists of gravitational potential energy of the body and the elastic potential energy of the beams. The body has 3 degrees freedom, x, rho, pitch, so the energy landscape also 3D. To find the best trajectory, we first make a network based on energy landscape. The vertices are states with different potential energy. The edges are the energy codes when the body moves from one state to another. From low energy state to high, we set the code is energy difference. From high to low, we set the code is 0. In this way, we get a non-conservative field. On the network, we mark the initial state and the target state, and we use Dijkström algorithm. We can find the mean cost path quickly. This path has the lowest potential energy barrier. Here is a planned trajectory in demo and its corresponding visualized trajectory. The stiffness of beams are high in this demo, and we can see our motion planning gives the same rolling trajectory as a cockroach to traverse when encountering the stiff beams. After we have the planned trajectory, we need to control the body to follow it. Here, we use the feedback linearization control. FQ are the physical interaction forces with beams. U is the control signal we get from the control method. It's trying to decrease the error between the desired state and the current state. And applying this control method in simulation, we can see the body can traverse the stiff beams successfully. Whether animals or robots, they have the sensory delay. Here, we swapped it to discuss its influence on traversal. We chose the stiff beams as example. So the body needs to roll to traverse. The images show the state right after sensory delay. The longer the delay, the more pitched up the body is when the start of the control. Using the above method, we can control situations well. They all roll to traverse high stiffness beams with the lower energy barrier.
2 minutes.
Thank you. So we run 20 trials for each and calculate energy cost for different sensory delay. And the statistical results show that although they can all traverse successfully, the shorter the sensory delay is, the more energy we can save. Here is a summary. First, we show the physical interaction helps the locomotor know the environmental physics like stiffness. And we also use a simple model system to demonstrate that we can use interaction to better plan motion and control. Finally, we discuss the influence of sensory delay in beam traversal. Next step, we'll use a robot to validate the above method and further explore this systematically with the robot and the model. My lab mate Yaqing will talk about this robot design in next talk. You can stay if you are interested. Thanks for your listening.